Well, look who it is. Somebody interested in learning something about compound interest, and we are going to be talking about that along with these other vocabulary words and phrases here. Make sure you understand these by the end of the lesson, and you'll be good to go with this lesson. So let's start off with some definitions here. First of all, hopefully we all have a basic idea of what an investment is. I'm not going to define that formally here, but an investment, we're just investing our money into something. We're trying to gain on the money we invested. And so a fixed investment is something we need to know. Fixed investment is an investment where the principal is guaranteed. Sometimes it's insured by the federal government. The principal is guaranteed, so you're guaranteed to get at least that money back. And then the interest is at a fixed rate. It's a rate that cannot change, that cannot vary. Interest at a fixed rate. And some examples of this. So e.g., for example, a savings account. Generally a pretty lousy fixed rate of interest in a savings account. I think mine has like 0.2% or something ridiculously small like that. Something called a CD, a certificate of deposit. Certificate of deposit. So not the compact disc, but CDs, certificates of deposit, generally have a little better rate of interest, but you have to keep your money in there longer. It's not very liquid, we call that. We can't just go there and say, hey, I want this money right now. They'll say, I'm sorry, you agreed to leave it with us for a certain designated amount of time. And then a savings bond, often you'll see savings bond backed by the federal government or given by the federal government. You can buy a U.S. savings bond, something like that. And that is at a fixed rate. You're guaranteed to get your money back plus a little extra for the interest. And then a variable investment, just like it sounds, it's variable. It varies from one investment to another, from one person to another. It can go up or down. You're not guaranteed anything. So neither the principal, so the money that you first put in there, nor the interest is guaranteed. So you might be asking yourself, why the heck would I put my money into a variable investment then? Well, you have a better chance, or a higher probability, I guess I could say, of making more money. That's why people invest their money in variable investments. Fixed investments, usually they're not risky, but they're not risky at all, but you don't get as much money back potentially on your investment. So variable investments, sometimes you take the risk and it doesn't pay off, but sometimes it does. So stocks are generally a little more risky. Mutual funds, something where they pool their money together with a bunch of other people that want to buy stock, and then they invest money in all these different companies with mutual funds, and a little less risk with mutual funds than with straight up stocks. Commercial bonds as well. Alright, so less risk with mutual funds, but potentially less reward for the most part too than stocks. If you invested in the stock of, well, they didn't have stocks until recently, but Facebook recently just sold stocks. But if you would have invested into Facebook as it was first starting up, you might be a very, very wealthy person today. And then one other thing, compound interest. Excuse me. Compound interest. And thinking about Facebook again, that variable investment, you weren't guaranteed the money back if you would have given Mark Zuckerberg your money at first, but if you had partnered up with him in the early days, you would have been a very, very wealthy person, I would say, by this point. Compound interest, though, it's compounding. It's like interest upon interest. And I want to get this quote right, too, just a second. There's a quote from Ben Franklin that I really like in the book here. It says, or he said one time, that money makes money, and the money that makes, let me start over with that. Money makes money, and the money that money makes more money. There we go. And so that's what compound interest is. You're making money on top of the money that you're earning with interest. So you're making interest on interest. in a sense. So it's the interest computed on principal and accumulated interest. So the interest goes back into the account or whatever kind of investment you have that stays with the investment, and you get interest on top of that. Then every time, whenever the compounding period is, every perhaps year, every month even, every day, every quarter, it kind of all depends. Accumulated interest, there we go. So interest computed on principal and accumulated interest. And then the big thing for this lesson. In the previous lesson, the big formula was I equals PRT. And I'm going to remember that as I, PRT, kind of sounds like party, so I'm going to say like I'm going to a party, I party. Alright, so, oh, that's there. And I put this down here, I meant to put that up there. Whoops-a-daisy up here, there we go. So that's going to go right there for me. And let's fill that out now. So compound interest formula. What is the compound interest formula? It's a little more involved than the simple interest formula because there's more going on. You're going to take your money and invest it. We will potentially be taking a look at where this formula comes from or how you can derive the formula, but for the sake of this video, we're not going to do that right now. We're just going to accept this as the formula. So it's principal equals, or the amount equals a principal times, then in parentheses 1 plus the rate over this n thing. We'll talk about what n means in a second, and then n to the nt power. So what are all these things standing for? This is where a is going to represent the amount, the total amount that you have in the account or investment after you're done with it. So this is the amount, total amount. That's where the A comes from the amount. P, that's a lowercase p. The P standing for the same thing as before, the principal, the amount you originally invested, the principal. R is the annual rate, just like before. So it's annual rates of interest. T is going to equal the time, and the time is in years, just like before as well. Time was in years. And this N, this is the new thing here along with the A part. N is the number of compounding periods per year. Number of compounding periods per year. So let's check out an example and use this formula in this example. So example 1, we'll talk about why Albert Einstein is in that picture in just a little bit. So at the age of 18, you decide to put $1,000 in a retirement account. It's never too early to think about retirement. Alright, so somebody once shared some information with me about retirement and said if I invested money into a retirement account really early, it would really be helpful. And so I kind of listened to their advice and I started doing that when I was younger. Not quite 18 necessarily, but pretty close to that. And so we've got this $1,000, and we've got two options. We're trying to explore our options and decide which one is the better option. Option 1 has a simple annual interest rate of 5%. And I'm going to write with no compounding. So you are not, the interest that you earn does not go back into the account. So no compounding. And option 2 has a rate of 4.5% compounded quarterly. So this one does compound, and it compounds quarterly. So think about what quarter means, and that should hopefully ring a bell from previous experiences you've had. So which option will make you more money? If you retire in 47 years, we're going to say. So fairly normal retirement age. To add 18, add 47 to that, and you're going to be 65 years old. And so let's figure out our options here. So I'm going to split this up into two separate parts. Option 1, option 2. Option 1 will go over here, and option 2 will work out over here. So option 1, this is a simple annual interest rate of 5%. And so go back to here. This is a simple interest formula. We're going to use I-PRT. So I equals P R T. And the principal is $1,000. So that's going to be your P. The rate for option 1 was at 5%. So we changed 5% to a decimal. It's 0.05. And the time in years is 47. So take a calculator at that point and figure out what that is. So this will be 1,000 times 0.05 times 47. And that all equals $23.50. So the interest is $2,350 on that. That's not your final answer. You want to figure out what your total amount in the account is. So this one, I'm going to say the total here, that's P plus I, the principal plus interest. So you have $1,000 originally plus the $23.50 that you made in interest. Not bad there. You made $2,350 and you only started with $1,000. So you more than doubled your money. Very nice. You're at $3,350. Okay, so let's circle that. That's not a final answer, but that's one of our two options. That's a very vital piece of information to figure out the answer, final answer to this problem. And now the other one. So option 2, we're going to use this compound interest formula. We're going to plug in P, R, N, and T, and A is representing the amount in the account at the very end, or in our investment at the end. So principal. Let's write down the equation with the variables in there. So we're going to write it down like that first and then plug stuff in. So R over N and then NT. And what's going in where? Well, take out a different color at this point. I'm getting out my red here. You see that word quarterly. What should you think? Quarterly is how many times a year is that going to be? Every quarter, that would be 4 times a year. So 4 quarters in a dollar, 4 quarters in a year, 4 times a year. That's going to go in for the number of compounding periods. That goes in for N right there. That goes in for N right there as well. It's the same N. Same value going in both places there. So we are going to replace this with 1,000. It's the principal. We're going to place R. The interest rate here is 4.5% in this option. So change this to a decimal and write it like that. And then your N is a 4. So 4 times a year, that gets put there, and you put it 4 times, this is to a power, so 4 kind of up towards the top, kind of small, times how many years? Still 47 years. So we're going to take a calculator for sure. We'll need a calculator for this, because I'm going to be taking a power, I'm going to be raising this, looks like, to the 188th power. If you want to multiply this decimal by itself 188 times, you'd be my guest. I'll see you at the end of the school year or something like that. Not much fun there. Thank goodness. I was going to say thank heaven, but thank heavens for 7-Eleven. Thank goodness for calculators. So before the advent of calculators, they would have had to done that calculation by hand. Really tedious right there. So we're going to take this divided by 4, and we have 0.01125. So we have 1.01125 if we add 1 to that value. And then this will be to the 188th power. So take your calculator back out again. We're going to take 1,000. If your calculator lets you do, or if it knows order of operations, lets you punch in the whole thing at once, great. That's a good calculator to have. Hopefully you have something like that. If not, you're going to have to do it one piece at a time, thinking of order of operations. So this raised to this X to the Y button, some of you may have a Y to the X button instead, or a little caret even. That's going to be our power button. The caret looks just like that. What I typed in right there gave me a little caret symbol, and then this is 188. 1888, 188. So this will, my calculator here knows to take this to this power first and then multiply it by 1,000 because it knows order of operations. And so this becomes wait, what? Was that right? $8,192.27. I had a lower rate of interest and I made more money? Are you serious? I made that much more money? That's almost $5,000 more. I don't get that. That is the power of compound interest right here. This guy, Albert Einstein, he was once asked to reply, or asked to name the greatest discovery of man. He said this: the greatest discovery of man was compound interest. That's how powerful he knew compound interest was. So compound interest is incredibly powerful, incredibly useful, especially if you keep your money in an investment for a long time. It's going to keep compounding more and more and more, and you'll just get more and more money in that account. So what's the better option? Clearly, option 2 is going to be the one that's going to make you more money here. So option 2 clearly makes you more money. Now, hopefully you don't think money is everything in life, but hey, I want you to be wise with your money. I want you to spend it wisely, invest it wisely, and I want you to make good decisions with that money. This would be the better decision by far, because you know the power of math, you know the power of compound interest. Now you know, wow, I should really check out if something has compound interest as compared to just simple interest without compounding. Definitely check out the difference between the two and see which one would make you more money. So this, if we extended that idea out to, let's say, somehow you were able to keep it in there 100 years, or maybe you invested something for your grandkids or great-great-grandkids and they didn't know about it, and you put in, you had the same rate of interest, but you were going to do that to the 100th power instead for 100 years. Let's just see what that would be, just out of curiosity. So 1,000 times, you'd still have this if it was at the 4.5%. So times 1.01125, not 111, 1125, and you're going to raise that. So if we're talking 100 years, you would raise that to the 100th power. Man, this keeps doubling up things. I'm only touching it twice and it does it 3 times. But let's see what you'd get. How much money would that be? $1,000 invested originally at 4.5% compounded quarterly for 100 years. That's not right. What a letdown there. Yeah, now I feel like a total idiot. So 1.01125 to the, did you see my mistake there? I just did it to 100th power, but it's going to be the 4 times 100, so it would actually be 400 because you're compounding it quarterly. That has to go there. So 400, there we go. $1,000 originally. Put it in the account for 100 years. You're going to have $87,783. Pretty ridiculous, pretty insane. If you want to read even more about the power of compound interest, check out page 614 in your book. There's a little blurb about the cost of the island of Manhattan. Back in 1626, it was purchased for $24. And if that would have been invested, $24 invested at 6% interest for or however many years, that was 378 years, the book says that investment would now be worth, depending on how much it was compounded annually or continuously, you could actually compound continuously, it could be worth millions of dollars at that point. So pretty crazy. Check out the book to see exactly how much. Alright, so let's check out example 2 after we define one more thing here. So the effective annual yield. Effective annual yield. Can you hear that cricket in the background? I hope not. I got a cricket outside my door here. So effective annual yield. I'm here at school making the video and there's a cricket. They seem to like just outside my door for whatever reason. So that, or the annual percentage yield. Sometimes you hear that called the APY. So this is a little advertisement I found on the internet. There's a bank, Sovereign Bank, I think this was called. And so Sovereign, they're advertising this 3.00% APY, annual percentage yield on the money. So what is the definition of this? This is the simple interest rate that gives the same amount of interest as a compound rate over the same period of time. And so let's check out an example to make a little better sense of that. So let's determine the APY, the annual percentage yield. Usually we'll call it that instead of the effective annual yield, but they both mean the same thing. Determine the APY for, when we determine APYs, we're always going to be thinking about investing just $1. So $1 invested for, and also for 1 year. So we want to keep those numbers just plain old ones. $1 invested for 1 year at 3.7%. Compounded daily. So you should think compounding daily, that's probably a little better than compounding like we did here quarterly, and you'd be right. So how much better is it? Well, it kind of depends on how much the percentage is. But let's check this out and see what we got. So we're going to go back to this equation here. This is the big daddy in this lesson. So A is P, A equals principal times, and then 1 plus the rate over the number of compounding periods to the n t power. Alright, so we have, what's my principal? I'm investing $1, so I'm going to replace the P with $1. And I'm going to put this as 1 plus, this becomes 0.037. That's just that as a decimal. Daily, compounding daily. What does that mean? Get out your different color here. I want you to underline daily in your different color, and I want you to connect this over here to this part in just a second. So 360, for the purposes of calculations, we're using the banker's rule here. We're saying 360 days instead of 365 or 366. We're going to say 360 days in a year. For our calculations, that's what we're doing here for the APY. And so what do you get when you work this out? So this becomes, you still have a 1 out in front here. Then you'll be multiplying this by, and actually I'm going to just go ahead and calculate this all at once. I changed my mind on that. So I'm going to plug this all into a calculator right at this point. So I'm going to take my calculator out here. The 1 out in front is not going to have any effect on multiplying it through here, because that will just keep it the same. It's like our identity element for multiplication. We'll hold a little throwback to our previous chapter there, the identity element. And so we're just going to do 1 plus and I actually wanted to put this in parentheses. So I want to do 1 plus, I'm going to do this all in one shot, show you how you can do that. If you want to break it apart into different parts, that's fine. 360, and now I will close my parentheses. So that's what that is inside of there. And then from there I want to take that, and you can see that that would not have been very fun to do longhand, but I want to take that to the 360 power. So 360 times 1 is still 360, and so that'll raise that number to the 360 power, and so I get 1.03769, so on. Usually we'll go with 4 decimal places if we're going to round this percentage type stuff here. So we're going to go 1.037, and this will be rounded up to a 7 because that next digit is 5 or higher. So about what you see there, what you saw there. Try that on your own calculator too, just to make sure you get the same thing. Make sure you know how to use your own calculator. So 1.0377 approximately, and that's going to be the amount of money I would have in the account total afterwards. So like $1.03 and like partial cents, 7, that part of a cent. So the interest is just that amount minus the principal. So the amount was this, the principal was 1, and so we take that minus 1, we're just left with the decimal part of that. So 0.0377, or approximately, these were all approximate, so I'll change those to approximately equal 2 signs. Those are rounded off just a little bit. That's about 3.77, and so not much higher than what you saw there, but every day it's getting compounded. This is the effective annual yield, or in other words the APY, the annual percentage yield. And so this, maybe they had a compounding, they could have done like 2.9, maybe compounded every week or something like that, and maybe got to 3.00 APY. So APY is really the one that matters, that counts the most. If they say 3.7 compounded daily, the APY is what you're really concerned with. So let's do one more example here, and if you know your nursery rhymes, you might know who this could potentially be. This is going to be Jack and Jill. Why they're going up the hill instead of down the hill to fetch a pail of water, I don't know. I just was thinking about that today, and you would think the well, I don't know if they're going to a well or the stream would be down the hill instead of up the hill. Maybe there is a well though. Maybe they have a well up the hill. That's the only thing I can think of, or a little stream or a spring or something like that. But shouldn't have been going up that hill. Jack and Jill Hill, we're going to say Hill is their last name, they would like to have, well, college expenses. Tuition keeps rising year after year after year. They're thinking we need to have at least like $37,500 a year for our kids. Multiply that by 4, they thought, okay, we got to have $150,000 for their newborn child. So in 18 years, to pay for their newborn child's college education. So they are considerate parents. They're thinking, okay, if our kid wants to go to college, we're going to try to help them out by doing this. How much should they invest now if they can secure, if they can get, kind of in other words there, if they can secure a fixed investment, so no risk investment, money is guaranteed, no risk fixed investment, that has a rate of 4.15% compounded semi-annually. So first of all, let's talk about this word, different color for this one, and say what that would mean. So semi-annually instead of quarterly, this is semi, like a semicircle is half a circle. Semi-annually would be half of a year. So this would be 2 times a year you'd be compounding that. So let's just put that in a different color. Just a little side note there as to what that's referring to. Go back to your formula here. And so we're still going to use this. A is P times 1. Principal times parentheses 1 plus rate over the compounding periods, and then the compounding periods times the time to that power. You could arrange this. You could actually, I'm just going to verbally say this, but you could take this, I could divide by P, I'd get A over P. I could divide that part by A, and I'd have 1 over P equals this whole thing over A. And then I could flip-flop. I could take the reciprocal of both of those things, and I would end up with this. So knowing how that all works, that's not super important to me, but that's an explanation of where this formula comes from. This, what they call the present value formula in the book. So this is 1 plus R over N. That stuff all stays the same, and nothing changing here. So here, this time, the P is unknown. The principal is unknown. How much you're originally going to put in there, we don't know. Write this in a different color off to the side here. How I got to this was, I'll re-explain or write it down here. I'm not going to force you to know how I go from this step to this step, but I do need you to write this down for me right now. So this is where this came from. I think it's important that you know where formulas come from whenever possible. That makes it a little easier to remember what they are in the first place. So dividing both sides by both P and A, and then taking the reciprocal, yields this, what you see there. And so this is called the, let's write this off to the side. This will put in our normal color, the present value formula. They call it that because we're going to use this when we're asking the question, what's the present value of the money that I need to put into an account to have a certain amount later on in life. And so this P is representing the principal or the present value in this case. So the present value for this problem in particular, the amount you want on the top is $150,000. And then you're going to be dividing that by 1 over, the rate is 4.15, so this will become 0.0415. Divide that by semi-annually, but divided by 2. So that's the number of compounding periods. You're taking this to the 2 times, what is the time? 18 years. So we're going to say that's ready in 18 years. So 2 times 18 here. So this becomes 150,000 over, and this, if you put this into a calculator, let's do that right now. We have 0.0415, divide that by 2, and you're going to get this. So you have a 1 in front of that with the 1 right here. You have a 1.02075. That's what's in the parentheses. You're going to be raising that to the 36th power, 2 times 18. So at this point, we can think of this problem in 2 different ways. You could do this to the 36th power, or you could just do the whole thing all at once. That's going to be the best answer if you do the whole thing all at once. So let's do that here. Divide this by, and then again, your calculator, if it knows order of operations, you can type it in like I'm doing here. 1.02075. If I raise that to a power, it knows to do the power before taking this divided by that on the bottom. If your calculator doesn't know our order of operations, then it will do the division first. That would be a bad thing, and then raise it to the power, get the totally wrong answer, or something like that. So this raised to the 36th power does all that at once. And so this would be the best answer. You would say approximately $71,613.23. And so that right there is the best answer. Let's say you decided to do this though instead. You went and just figured out 1.02075. You raised that to the 36th power, and you got this number first. And you decided, oh, I'm going to round off to four decimals like Mr. Wagner usually says we should do with problems like this. So you'd have 0.045 or 0.0945 will get raised to a 6 because of that digit right there is 5 or higher. The 8, so we'd have 150,000 divided by not 2 or not 1 but 2. Bring that up again. 2.094, and that again was a 6. So let's say you rounded that to 4 decimal places and then put that into a calculator. Let's see how much different that would be. And so if you had this divided by 0.2, whoops, it's the 9 there we go. I do that and I get $71,612. And how many cents was that? 72 cents. So very, very close. You're talking about a difference of about 50 cents there. Not much at all, so 51 cents. But I would accept either answer unless I specifically told you to give the best possible answer. This would be the best possible answer. This one would be rounded off just a little bit more. So let's put that off to the side. This is actually the last thing we're going to write here. This is the last example we're covering. So this one right there is the best answer. This one right here is still a pretty good answer, but you rounded a little early. So this is your answer with rounding early. So put all that stuff in different colors here just to make things stand out a little nicer. I think it really helps having things in a different color to know. This was the main part of the problem. These are just some side notes. And that should do it. That should do it for us. Look at the book, as always, and check out some of the extra examples there. There's one more like this in the book. There are 2 more like this one in the book. And there are 2 more like this one in the book as well. So check out that. Check out plenty of other examples in the book to see more things like you saw here. If you're struggling with any of those things, let me know also in class if you have any questions. And have a good evening, morning, afternoon, whatever you're watching this. Have a good whatever. All right. Catch you guys later.